Hello, this is the second question on the class project. So for the first part of this is we are to determine if the capability of the process regarding the indicated dimensions, the specifications. So first, I'm going to find the LSL, which is the lower specification limit. That is 10.55. Says if you go to this correctly, we are at 10.70 plus slash minus 0.15. So I'll just disregard that for now. So the upper specification limit then is 10.85. And from there, so then the target itself is 10.7. So in order to find the upper and lower CP, we need to find the standard deviation for the equations. So what we're going to do here is, standard dev s. We're going to do this entire sample area. I'm going to hit enter, and we'll trim that number down a little bit. 0.87. Do that. We'll go from there. Okay, so the CPL has an equation of the mean minus the lower specification limit over 3 sigma. So we need to find out the mean of this entire sample area before we go any further. So we'll type in geomean, and okay, voila, 10.7. Okay, so like I said, it is the mean minus the lower specification limit over 3 times the standard deviation. Comes out to 5.82. The reason why we're looking for process capability on this is to see if a product meets the specifications. So we can only display this when the process is in control or not. And unfortunately, this can't be done on the IMR chart due to outliers. So what we're trying to do here is just see if these samples, the samples we have here are in control, let's just say for a customer or a production line. So we're going to find the CPU now, which is just a little bit different of an equation than the CPL. So it is the upper specification limit. The upper specification limit minus mean over 3 times the standard deviation. Enter 5.65. All right. So now, in order to get the CPK, all that is whether the CPU or the CPL is the min value. So for this, it would be the CPU. So the reason why we're going with CPK is because CPK is more reliable than just the CP. So we'll find the CP just to show you the difference. So the CP is, all right, equation is your upper specification limit minus your lower specification limit. And that is over, so instead of 3 sigma, you're doing an entire 6 sigma. And you're going to multiply that by your standard deviation. And there we go. So you can see that it is just a little bit different, a little bit higher than your CP, but within the range of CP, L and CPU. So now what we're looking for is that if our CP is less than 1, or if it's your CP is less than 1, then it is not capable. So right off the rip, we can determine that the CP is less than 1, therefore not, if I can spell, it's not capable. Let's just highlight that red for right now. We'll highlight that red. So going forward from here, we need to determine, what's the second portion of the, provide the non-conforming percentage of defective parts. So what we're going to do here is we're going to type in below SLW, and then above upper specification limit. Okay, so what we're doing here is we're trying to find out how many of these items right here are below 10.55. So we're going to use an Excel equation, count if parentheses. Now you do have to do the whole range of this entire bit right there, comma. You do the criteria, which is less than 10.55. And let's see what this comes out to. 0. Up here, right? Let's just type it in, see if it comes out any different. 2. There we go. Okay, so 2 of these numbers are below 10.55. So let's just take a look to see if we can find any. There's one. Just double check our work relatively quickly. there's the other. Okay. So now we are going to do the same type of equation for the upper portion as well. So we'll do the range. Then we're going to do the criteria. So we're going, whoops, 10.85. All right, let's do this one. Now to 8. So we have 8 items above 10.85. So yeah, you can tell the process is not capable with 10 being above or below the specification limit. You know, just looking through them, there's one there, there's one there, it's 2, 3, 4. I won't go through the rest, bog this down, but what we're doing from here is we're going to find out how the percentage of defects we have. So that's just a simple equation of 10 divided by, well, first let's see how many there are here. 120. Okay, so equals parentheses 10 divided by 120 divided by 100. And let's move that to percentage. That doesn't seem right. Just delete that. Oh, I know I did it wrong. Equals. That is divide instead of times. That is not right either. That should be 8.33. There we go. This should be roughly 8% of the total items in this 120 sample are deemed to be defective.